Good afternoon, everyone. Today we will study Chapter 6. It's about the inverse functions. Since some of this topic in these chapters we have already studied in the last semester, so we will go through a little quick in the Chapter 6. In this chapter, we will study inverse function, the logarithm and natural exponential and natural logarithm, and the inverse trigonometric functions, like those. Now, let's start from the inverse functions. So, examples about one-to-one function. Now, if we showed the rules, okay, the rules of the function f and g both, so we can assign the f for those elements 1, 2, 3 in the domain, right? 1, 2, 3 we call the set A is called domain and set B is called range. So the function f assigns the element 1, 2, 3 to the element in the range. Assigns 1 assigns 2, 2 assigns to 4, 3 assigns to 7, 4 assigns to 10. So f is a rule, f is a function, right? F is a function. And here for g, the function g assigns 1, 2, 3, 4 in the domain, assigns each element to the element in the range B, set B, right? But here we will notice that when we have the element 3 and 2, they assigns to the same element in the range, that is 4, right? So this is the two functions, right? Examples of two functions, f and g. Which one is one-to-one and which one is not? So what does one-to-one function mean? One-to-one function means if the elements in the domain are different, then that will assign to the different element in the range. So here 2 and 3 are different in the domain, but they assign to the same element 4, right? In the range set B. So here we can see that f is 1-to-1, but g is not. So that is the one-to-one function. We use the assignment, right? Here, assign one set exactly to another set, then it's clear to tell. Now, let's check the definitions of a one-to-one function. A function f is called a one-to-one function if it never takes on the same value twice. That means whenever x1 and x2 in the domain are different, then the function value also different, right? The function values are also different from each other. So from this graph, from this example, we can tell that this function f is not one-to-one, because here in the graph it shows x1 less than x2, right? Here x1 is less than x2, but so which means x1 and x2 are different, but their function value are the same, right? Their function value are the same. So f is not one-to-one. So that means the x values in the domain are different, then the function value are also different, which means one element in the domain will exactly assign to one element in the range. and a different element in the domain will assign a different element in the range. It's like that if we recall the graph. Okay, and what is the test we can use to check whether a function is one-to-one or not? Horizontal line test, right? Horizontal line test to check whether it is a one-to-one function. A function is one-to-one if and only if no horizontal line intersects its graph more than once. So it will intersect its graph at most once, right? Maybe no intersection, or maybe only once. It could it could not happen for more than once. So that is vertical line test. Okay, and be careful of the word if and only if we mentioned in the series, right? In the series part before. Now let's look at those two examples. Function fx equals x cubed, is it one to one? Gx equals x squared, is it one to one? Let's draw the graph and check it. So f is x cubed. Let's draw x cubed, xy coordinate. So here fx equals x cubed. Example 2, gx equals x squared. If we can get the graph, it will be easy to tell whether a function is one-to-one or not using the horizontal line test. Okay, so we can draw the horizontal line. You will notice that the horizontal line will always intersect the curve y equals x cubed only once. Okay, only once. How about the parabola x squared? If it's below the x-axis, no intersection. If it's above the x-axis, that will intersect twice, right? Intersect twice. So f is 1-to-1, y equals x cubed. But parabola is not, right? Parabola is not, because it will intersect the horizontal line more than once, right? More than once. So that is pretty easy, right? Pretty easy. And let's recall what is the vertical line test. Vertical line test comparing with the horizontal line test. What is the purpose of vertical line test? Vertical line test is to check whether a curve is a function or not, right? To check whether a curve in the x or y plane is a function or not. So be careful of those two, right? Those two tests, vertical line test and the horizontal line test. We have already studied this part last semester, so I will go through a little quick. The inverse function, the definition of inverse function. Let f be a one-to-one function with domain A and range B. Then its inverse function, we write it as f inverse, has domain B and range A, and it is defined in this way. We express x using y, right? To rewrite x equals an expression of y or a function of y. And here the f inverse is the notation for the inverse function, right? F to the exponent minus 1. This is just a notation for the inverse function. It does not equal to 1 over f. Okay, it's not 1 over f. Be careful of this attention, okay? Attention. And here the set A, let me write the set A and B, okay? So set A is the domain for the function f, and set B is the range for the function f. But for the inverse, then the range becomes the domain for its inverse function. Sorry, I should write here. So the set B becomes the domain for its inverse, and the set A becomes the range for the inverse function. And when we talk about a function has its inverse, then it should be 1 to 1. Okay, it should be 1 to 1. And when we call the inverse, actually f and f inverse, those two, they are inverse to each other. Okay, they are inverse function to each other. They are inverse functions to each other. What does this one mean? F inverse, this is also a new function, right? F inverse. What is the inverse for this function? It will come back to that function f, okay? The inverse of this function, that will be function f, okay? That will be function f. That's why we said they are inverse to each other, okay? They are inverse to each other. So that is the first section, the inverse functions. In the section 2, let's look at the natural exponential functions. We have already started the exponential functions, a to the x, right? A to the x, and when a is between 0 and 1, let's recall a little bit. So the exponential function, the general exponential function, that will be fx equals a to the x, right? Fx equals a to the x. And when the a is between 0 and 1, when the base is between 0 and 1, the exponential function will be decreasing, right? Will be decreasing from minus infinity, right? From minus infinity to infinity. And by the way, here the domain for this function will be all the real numbers, right? Will be all the real numbers. So when a is between 0 and 1, it's decreasing, and of course here is 1. That means when x is 0, the function value is 1, right? And if a is greater than 1, then that will give a increasing, right? Increasing function. And here, of course, it's still 1, right? It's still 1. So that is the exponential. And we will look at the natural exponential. Natural exponential means the base is e, natural number. The natural number e is greater than 1, so that will be this increasing one, right? That will be this increasing trend. So let's check the natural exponential function, okay? And let me just draw a graph to remind you the increasing trend. And intersect 1, right? Here is y-intercept is 1. Y equals e to the x, right? E to the x. So from here, okay, from here we can check that the domain of the function, the domain of this, The domain of this natural exponential will be all the real numbers, right? Will be all the real numbers. So the domain for the natural exponential will be minus infinity to infinity. How about the range? How about the range? You can check that the curve is always above the x-axis, and it will get very close to x-axis as x approaches minus infinity. So it will be positive, the range, right? It will be positive, the range. And we can check this limit, okay? We can check this limit. So the exponential function f(x) equals e to the x is an increasing continuous function, of course continuous, with the domain all the real numbers and the range is positive, right? How can we understand those two limits? When x approaches minus infinity, this curve will get very, very close to the horizontal axis but never touch. What is the function value? What is the y value? Of course, it's 0, right? The limit will be 0. And as x increases without bound, as x approaches plus infinity, then the function value will increases without bound, right? Will increases without bound. So that will be positive infinity, the limit. And since the curve, the natural exponential curve get close to the horizontal axis, but it never touch, what is the name? Horizontal asymptote, right? X-axis is called the horizontal asymptote for the natural exponential functions. Okay, so that is the review for the natural exponential function. And the derivative of this one is pretty easy. Gives the function itself, right? And that means what is the nth order of the derivative you take? It's always the function, right? For example, if you take the fifth, right? If you take the fifth derivative of this natural expansion, it's also this function itself, and the nth order, it's always the same. And according to this one, we can write its indefinite integral, right? So you can also say that the e to the x, the natural exponential function, its particular antiderivative also gives e to the x in indefinite integral plus the constant c, right? So this is very easy derivative and definite integrals for the natural exponential functions, okay? And the next one we will look at the logarithm functions, okay? Logarithm functions, and especially we will look at the natural log, okay? Natural log. And also we have the graph, okay? We have the graph. So let me write here. So for the logarithmic function, let's show the graph first. Logarithmic functions. So f(x) is log base a to the x, right? Actually, we can understand this is the inverse of the this is the inverse of exponential function, okay? This is the inverse of exponential function. For example, okay, we can write in this way. So my function is y to y equals a to the x, okay? A to the x. So you can solve your x. You can solve your x with the log base a y, right? So they are inverse to each other, right? They are inverse to each other. And how about the graph of the logarithm function? And we can check that the domain of the range, okay? So let me write f(x) equals a to the x. then f inverse, okay, f inverse function will be log base a x. So the domain and range, I want to mention the domain and range for those two functions. So for the exponential, we know the domain is all the real numbers, and the range will be positive, right? The range will be positive. And we know the graph when a is between 0 and 1, when a is greater than 1. So the domain for the f becomes the range for its inverse function. And then the range becomes the domain, okay? So when we talk about the logarithmic function, then the domain will be x is positive. Okay, of course the base a can be a positive number, can between 0 and 1, also can be greater than 1, right? So if it's between 0 and 1, okay, if it's between 0 and 1, that will give the increasing trend. So this is y equals a to the x when a is between, sorry, log, it's about the logarithm. This is the logarithm function. So should it be log x, and my a is between 0 and 1. And then let me choose a different color. So when a is greater than 1, that will be increasing trend, okay? This is y equals log a x when the base a is greater than 1. And let me show the coordinate. So we establish the xy, okay? xy, and this point is 1. When x is 1, that's 0. Okay, that's when x is 1, the function value gives 0. So it's the same as the exponential function. When the base a is greater than 1, it's increasing. When the base a is between 0 and 1, it's decreasing. And especially we will look at the natural log. Okay, natural log means the base is e, right? The base is e to the x. Its inverse will be log with the base e, so we are going to use log. Okay, we are going to use log. And for the log function, it's the same here. The domain is positive, and the range is all the real numbers. Okay, all the real numbers. Now let's start with the logarithmic functions in section 3. So for the natural log, okay, we can take the natural log as the inverse of the natural exponential. Okay, natural exponential. And as I mentioned, the domain for this natural log function will be sorry here. Okay, let me write here. Fx equals log x. So here the domain is the range for the natural exponential, so the domain will be positive, right? Will be positive, and the range will be all the real numbers. And there are some special values, okay? There are some special relations. So ln e to the x, ln e to the x. Here we look at this e to the x. For the natural exponential, this x is all the real numbers, right? This is the domain for the natural exponential function. So the x can be all the real numbers. And ln e to the x, you can rewrite it as x times ln e. And we know that ln e is 1, right? Ln e is 1. So ln x times ln e, that equals x, but this x is all the real numbers. And if we write in this way, e to ln x, e to ln x. This x is defined in the ln function, so that will be the domain for the ln function. That will be positive. Okay, that equals x, right? E to ln x, and also we have another result is e to ln 1. That is 1, right? When x equals 1. But here, this x should be positive because that is the x defined in the norm function. So that is the domain, right? So be careful, okay? Be careful. That is the natural log, okay? Natural log. So how can we change the other base a into the base e? So we have change of base formula, okay? Change of base formula. Ln x over ln a, okay? Ln x over ln a. And let's talk about the derivative, okay? So change of base formula, let me write it here, okay? Change of base formula. Log a x equals ln x over ln a. So here ln a is the constant actually, right? Ln a is a constant. You can take it as a fraction, a constant fraction times this ln function, right? 1 over ln a is a constant, right? It's a constant. And we know that the derivative of ln x gives 1 over x, right? Gives 1 over x. Then how about the derivative of log with the base ax? What is the derivative of this one? If we know ln x is 1 over x. So we can use the change of base formula to rewrite this function with the base a as 1 over ln a times ln x, right? And then since 1 over ln a is a constant, we can move 1 over ln a outside. Then that means take the derivative of ln x. Of course, the answer will be 1 over x times ln a, right? 1 over x times ln a. So we can also get the derivative of a logarithm function with any base a, just 1 over x times the fraction 1 over ln a, right? And here when we have the derivative, when we mention the ln function, of course here this x should be positive, right? That is defined, the function is defined, which means we should mention the domain for this x. But if we mention the definite integral of this 1 over x, for this one 1 over x, x can be all the real numbers except 0, right? X can be all the real numbers except 0. When we mention this x, 1 over x, this fraction is defined for all the real numbers except 0. So this x can be negative. When we take the indefinite integral of 1 over x, we know it's non-x, but here we should add the absolute sign, right? Add the absolute sign to make sure this part is defined, right? If it's a negative one, we should put the absolute value to make it defined for the natural log functions. Okay. And let's check two simple examples based on the derivative of ln x. Okay, and we know that it's 1 over x. Evaluate those two indefinite integrals, and of course we need the substitution rule to work it out. Okay, so here we have the fraction 1 over x squared plus 1. Okay, x squared plus 1, we can try let u equals x squared plus 1, then we can write it as 1 over u, right? So in this way, du over dx is 2x, right? 2x. So we can rewrite x times dx. That means you divided 2 on both sides, right? You shift the dx to the right side, and then you divide by 2. So x times dx is 1/2 du. Then let's evaluate this one using the variable u. Okay, evaluate the definite integral using the variable u. So that becomes 1 over u. X times dx, that becomes 1/2 du, right? 1/2 du. So I can move this 1/2 outside. Evaluate the definite integral 1 over u du. So follow the formula. We know it's ln absolute value u plus constant c, right? Indefinite integral should plus a constant c. Don't forget this constant part. And then we can go back. Sorry, we can go back to the x. We can go back to the x. So it will be 1/2 ln x squared plus 1 plus c. And you will notice that here my u is x squared plus 1. Of course, u is positive, right? U is already positive variable. So that will be ln. You can just put a parenthesis. There is no need to put the absolute value for this example because x squared plus 1 is already positive. So that will be 1/2 ln x squared plus 1 plus constant c, right? So that is part A. Now let's looking at part B. Evaluate the indefinite integral for tangent x. So that means some function's derivative or tangent x is the derivative for some function. We don't know so far, right? We don't know which function will give the derivative is tangent x. We only know the derivative of tangent x, but we don't know how can we find the antiderivative for tangent x. So we can write tangent x as sine x over cosine x, right? We can rewrite the tangent x as sine x over cosine x. So that becomes 1 over cosine x times sine x dx. 1 over cosine x, we can let u equals cosine x. Then you can write it as 1 over u, right? 1 over u. So du over dx, that is minus sine, right? That is minus sine. So you can rewrite sine x times sine x dx equals minus du, right? You can shift the dx to the right side and add minus on both sides. Minus minus becomes plus, right? So here, minus indefinite integral sine x over cosine dx. You can rewrite it as 1 over cosine x, then times sine x dx. They're the same, right? They're the same. So what is 1 over cosine? 1 over cosine is 1 over u, right? 1 over u. Sine x dx equals minus du. So that becomes minus 1 over u du. So that will be minus ln u, right? Ln u. What is my u? My u is cosine x, right? Plus the constant c. Here we should add the absolute sign, okay? U is sine x. We know the sine x, the range is minus 1 to 1, right? It can be negative. It can be negative. And of course here u should be between minus 1 and 1, but not equal to 0, right? And you can shift this minus 1 to the cosine here. That becomes ln 1 over cosine. 1 over cosine, it's second x, right? It's second x plus c. So here we use the formula cosine x minus 1, right? To the exponent minus 1. That is 1 over cosine. 1 over cosine x equals to second x. We use this relation, okay? We use this, we can move the minus in front of the ln function inside. That is cosine to the exponent minus 1. Then 1 over cosine, that is the same as secant x. Okay, secant x. So that is the natural log part. Okay, natural log part. It's almost time. Let's take a break. Then we will come back.